question. Will we be unable to use Visual Studio for the final project?
For the final sort of lab today? That is correct. So potentially anyone who wants to work on Windows, I do have a copy of the final binary to, I have it in my transfer folder. I ported it to Windows. The problem is Visual Studio is not so great for debugging. I guess it maybe can, but I've never actually tried. But I don't believe it's going to be appropriate for debugging like a straight up binary. And that's what I'm going to be giving you at the very end. Straight up binary with no source. So if I gave you the source for this final binary, it would defeat the entire point of figuring out what the inputs would be, right? So Visual Studio is good for debugging source and binary at the same time, but I want to give you just straight up binary. So if you have previous experience with Windows, you can use whatever tools you want, IDA Pro, WinDebug, OllyDebug, anything like that. Otherwise, I'd say most people, we should stick with GDB for now, just so that everyone's on the same page and I can wander around and help people out, etc.
Okay, thanks.
Yeah, so the reason I ported the binary to Windows is because ideally I would have liked to let people choose, do you want to do Windows or do you want to do Linux? But what I've found is that I can't shoehorn in enough description of WinDebug and all of its commands because every debugger has its own completely different commands. So, you know, if you're definitely interested in doing Windows at the end, since I'm going to try to get there faster today, we can potentially do some WinDebug, but otherwise it's probably best to just use GDB because it's really less about what tool you're using and more about understanding the code and figuring out what are the inputs it's asking for. How do I change these conditional jumps so that it goes one way where it, you know, succeeds, right? So, anyways, part 4. All right, lots of fun stuff here. Okay, so let's talk about inline assembly first. So inline assembly, right, now you've had plenty of experience looking at assembly. Now potentially you might want to write some of your own assembly, right? And like I said before, I think I said before, maybe think of the previous class, there are definitely things in kernel mode where if you're writing a kernel mode driver, you have to write inline assembly because there's registers for which there is no C way to access them. You literally just have to write an assembly instruction that says, you know, I want to move this value to a control register. I want to move this value to a debug register, right? You know, you know, implicitly when you write regular C code, yes, it'll be touching your regular registers, EAX, EBX, ECX, etc., right? But it's not going to like implicitly change stuff on control registers, things like that. C has no notion of x86 control registers, right? So therefore, in some cases, you have to write this inline assembly. Other cases I've found are where well, I'll get to there when I get there. And I think I mentioned yesterday as well, when Ariel was asking about like shifting left and shifting right, things like that. So I said there is like this roll instruction, which is like a bit shift where whatever comes off one side goes back onto the other side potentially. And those are used in cryptography frequently. Well, not frequently, occasionally. And so if you're writing some crypto library and you want to use roll within, you know, if roll is a part of your actual, you know, algorithm within the crypto, then you have no way of generating that. I think technically you can generate it through playing some, like, using your shifts and, like, using the right kind of shifts and things like that. I think it is technically still possible to do it, but I don't know for sure because I never tried. So, and, you know, maybe you think you're smarter than the compiler and you went through and you read the optimization guideline and therefore you know best what you need to do with your assembly. So go ahead and write it for that as well. But really, the big reason why I like having inline assembly in here is you can go back, take GCC, take Visual Studio, and, you know, just put in simple instructions and, like, see what happens. So you can write a small sequence of instructions in order to do something like, say you want to find out, you know, say you want, like, just a program which prints out the instruction pointer that's saved on the stack, right? How would you do that? Right? So you can do that. You probably need to read EBP plus 4, that's where that saved instruction pointer is, right? Move that into some register, and then potentially we'll see there's syntax to move a register into like a C variable. But a C variable is really just an EBP minus something else, right? So you could just take EBP plus 4, move it into a register, and then move that into EBP minus 4, or just push it and then call printf or something like that, right? So why even put it into a local variable? read EBP plus 4, push it, call printf. There you go. You have a program now which all you did was 2 assembly instructions. And, well, I don't know that the printf, the syntax wouldn't work, so you'd have to still use an assembly call as well. So 3 assembly instructions. All right. So we've got the different compilers / assemblers are going to require their assembly in different formats. So Visual Studio being a Intel syntax kind of place, you're going to put your inline assembly basically as a sequence of single Intel syntax instructions separated by a new line, right? So one on a line, move it down, do another line, right? So, and specifically there's __ ASM, curly brackets, and then your sequence of instructions, close curly brackets, and then a semicolon, where the semicolon is not strictly necessary, but it's good for keeping your syntax tab highlighting and all that good, so just put it there. So __ ASM, curly brackets, sequence of instructions, and yes, you could even put like labels and stuff in here if you want. That makes it much easier, right? Rather than doing a jump E, plus some number of bytes, it's actually, it's not really possible to do within the constraints of this inline assembler. It won't let you do like jump E, jump if equal, 5 bytes forward or something like that. Like if you put jump if equal 5, the assembler is going to say, aha, you wanted to jump to address 5, right? So in some of these cases, you have to use trickery to get the right kind of instruction that you want. So anyways, this is the syntax for inline assembly. You can write any sort of small little program inside your C program, and it's a good way to just experiment with things. Right? And, Visual Studio's inline assembly for dealing with C variables to go from, you've got your little snippet of assembly, and you want to put that into something that C can then manipulate, and you just want to do the rest in C. It's nice and easy. Just do something like move EAX to myvar, something like that. And so, or move, myvar to EAX. So you can get into and out of registers. Very simple. Just specify the C variable name, right? But the thing you need to know is that myvar, like what are variables behind the scenes? They're EBP minus something. And if you're going to move EAX, whatever's in EAX, into this variable, strictly speaking, right? The variable is in memory at EBP minus something. So the address of myvar is EBP minus 4. But the memory there is, you're behind the scenes, this is actually generating some sort of RM32, right? Because you're trying to store it in memory at the location for my variable in memory. And so behind the scenes, this is more like a move EAX into EBP minus 4 in an angle brackets, right? So that's why, for instance, you can't like use inline assembly to go move myvar1 to myvar2, because those are two memory things behind, and that would be a memory to memory move. And then also, sometimes you have to play little tricks with, you can't do like long strings of CD referencing and things like that, right? So you can't do like, a.var1, like remember when we had those structs before? You can't put like move EAX into a.var2 of 3 or something like that, because that's actually, right, we've seen when you access something like a.var2 of 3, it's a sequence of assembly instructions all like just itself, right? First you get the base of the thing, then you get the offset, then you write into memory, right? So you can do simple little things like memory to register, register to memory right here. But you don't be trying to throw huge long C. I know that my variable is actually this subvariable of this struct inside of another struct, etc. So simple variables only, please. All right. GCC assembly syntax, inline assembly syntax, AT&T syntax, as we would kind of expect, because the assembler in the behind the scenes is expecting it. And so here we have ASM, just ASM, no underscore like the previous one. ASM. Parentheses, and then we have quotes around each of these instructions, and we even have the /n new line like explicitly stated in these if you want to do more than one within a single ASM thing, right? So if you don't want the /n, you can just do ASM and then a single instruction between quotes, and then do another ASM, parentheses, single instruction between quotes. But because what the compiler is essentially going to do with this is the compiler is going to take this and it's going to grab that and it's going to it's going to maybe so sometimes it'll treat it like its own little thing, and it like won't think about that with respect to the rest of the assembly generated on each side, and it'll literally just take that blob of assembly and pass it to the back-end assembler. And other times, the assembler will treat that as, contiguous within some other stream of assembly, and it'll compensate for variables and things like that. So anyways, this is just the syntax, ASM, parentheses, quotes, and a /n if you want to have multiple assembly instructions in the same ASM chunk. All right. Now, this is where it gets a bit nasty. This is called the extended assembly syntax, or if you want to do something like we just saw in Visual Studio, where you put a register into memory, into a C variable. So if we're going into and out of C variables, you're now forced to use this extended ASM syntax. And the syntax here is ASM, parentheses, assembler template. This is kind of like a quoted, potentially it acts like a format string kind of thing. Okay, so think of it kind of like a format string. And then these other things at the end are kind of like parameters to that format string. So you've got output operands. So if you have something here, then something in that format string can potentially say whatever is here in the format string, that's going to go into output operand 1 or output operand 2, etc. And then you may have another format specifier that says, my input operands here, I'm going to put into this format string. So anyways, it's all very nice and ugly. List of clobbered registers. This is what you're saying, like, I want to, these are the registers which I know I'm going to be destroying so that the assembler can keep that in mind relative to the stuff on either side. So, all right, so again, simple. Say we have an int myvar in C. Now, if I want to move the value from myvar into a register, here's what I have. So now, all of a sudden, we have double percent signs, and this is what I have against percent signs I knew before. So a normal assembly instruction in Intel AT&T syntax, we have a single percent sign in front of it, right? Now this double percent sign is trying to say, like, okay, this is just a normal EAX. Don't treat it like anything special. But a single percent sign here for this percent sign 0, this is saying take my 0th parameter from my output operands or my input operands or something like that. So take something from one of these and put that in here. So it's like saying, okay, well, what's my, which side is this? This is my output parameter, right? So I'm trying to do a move EAX into myvar, right? So Intel syntax, EAX is on the left, move that to the right, trying to put EAX into myvar. %0 is saying replace this %0 with myvar, right? Because I've got this output operand over here, and so we need to like figure out. So behind the scenes, the assembler has to figure out like what is the output operand, and like it's again going to really it's going to do like EBP -4 or something like that, right? It's going to treat that like an RM32. It's going to stick that in there. It's going to generate move EAX RM32 EBP -4, right? But there's just this great syntactical way that you have to specify this. And you need this little equal sign, because that's like saying equals this register is going into this memory location and whatever. And then on the other hand, like if you're trying to take input from the variable, well, now I have colon, so this thing right here in the middle, so we have colon, output operands, right? And then colon, input operands. So there's nothing in my output operands here. I'm trying to take input, but I still have to have colon to separate and say, okay, the first colon, the stuff after that is the output operands. The second colon, the stuff after that is the input operands. Okay, so I have no output operands. I have only input operands. And that says, take this myvar, put it into this %0, and I'm trying to move from myvar to EAX. It's a literal EAX because it's got double percent signs. So there you go. Pain in the ass if you try to do anything complicated in this syntax. Typically, you end up just wanting to know behind the scenes, okay, this is, my var is, EBP -4. I'm just going to go find that out myself and just write the assembly instruction, right? Okay, I declared A and then I declared B, so B must be EBP -8, something like that. You'll find yourself not wanting to use C variables, basically. Right? So, fabulous. All right. Now, these are kind of useful in some cases. So this gets into that notion that we had before, where there is some sequence of bytes which are interpreted as instructions, right? Different bytes correspond to different instructions. So instead of doing inline assembly, in some cases, you may want to know, or you may find that I cannot get the assembler to generate the exact form of the instruction I want, right? So you went to the manual and you said, you looked through and you said, oh, call absolute indirect. Okay, well, I want to call, you know, RM32 EAX or something like that, right? And then you try to put that in, and you put like call, and then you put brackets, and you put EAX, and if that doesn't work for some reason, you know, you fight with it for a while, you try different syntax variations, whatever. If you ultimately come up with something where you can't get the assembler to generate the exact instruction you wanted, then what you need to do is basically hard code the bytes for that assembly instruction. And so I found this, for instance, like there was one time when Visual Studio wouldn't let me set one control register, but it would let me set another. So I could like do just a move. It was very simple. It was like move to control register 1 from EAX or something like that. And like it was fine with that. But if I changed control register 1 to control register 0, it was like, no, I don't know about that instruction. But it's like the exact same instruction, just a different variant, right? So I had to like hard code the bytes for what is this actual, you know, variant of the same instruction. And then other times, well, there was another case I can't remember at the moment, though. So, oh, right. So we may see it later, and we definitely see it in Life of Binaries, because I'm working on the virus for that right now, and I had to use this for the virus, and the virus isn't working, and it sucks. But anyways, there's like this form of like, so okay, for instance, that jump -2 that we talked about before, like that infinite loop, so jump 2 backwards. I feel like, no, maybe that one that is easy to do. So it's more like a call 0. So if I want to call 0 bytes from the next instruction forward, and so I call to the next instruction because it's 0 bytes offset from the next instruction. So call 0 is not something I've been able to get the assembler to generate for me in the past. So I just hard code the bytes for that. Anyways, so you have an emit and byte. So emit is the Visual Studio version, and .byte is the GCC version. So if I do __ ASM, and then I put in that _ emit hex 55, that hex 55 behind the scenes is actually push EBP. So push EBP is actually a 1-byte instruction specified by the byte 55. And I can also do something like, you know, I can just take 2 of those. I can put 2 of those in sequence. And then, you know, I'll emit byte 89 and then E5. And the sequence 89 E5 is move ESP to EBP, right? So you're if you looked at the bytes behind your typical function prologue, you'd see 55, then 89, 89 E5. So proving that, oops, that's not it. So remember we had our objdump. Objdump-D for disassemble. My example 2. S, right? First 2 instructions. We've just elided the fact thus far, but the actual byte sequence for that instruction is 55. That's the push EBP. 89 E5. That's the move EBP to ESP, right? So there's some sequence of instructions behind the scenes. If you find that you want to generate an exact instruction sequence, you like, I want this instruction, go ahead and hard code those bytes with an emit or a .byte. So different syntax for the same thing. So in the ASM one, at least the .byte, you can put a bunch of those all in the same ASM block. All right. So now comes the fun part, because I've repeatedly misled you, and it's time to read the fun manual. So this is by definition the fun part. Okay, so at this link, that's where the actual Intel manuals are. just the high-level overview is that Volume 1 is just kind of a summary of a lot of stuff. And this is actually where I really like to bring up, my stack of manuals like this big. But we're going to just be looking at the PDFs instead because I'm not bringing those with me on the plane. All right, so Volume 1 is the summary. It's just kind of like high level for a bunch of stuff for all of x86. Volumes 2A and B, those are like all the detailed explanations of all the instructions. And we said, in this class we've learned however many, 24, 27, something like that instructions. If you want, so it looks like 24. If you want to see all the various instructions which do, one little specific thing, you can go look at 2A and 2B to find those. And then 3A and 3B, that's all sorts of extra good stuff about, how virtual memory works, how segmentation works. That's stuff we get into in the intermediate class, but then also, the MMX instructions. Remember back in the day when Intel had their bunny, rabbit, dancing bunnies, MMX commercials? That's in there. It's all in the manual. The virtual machine extensions, right? So when we say that, nowadays x86 hardware has hardware support for virtualization, right? There's a bunch of extra instructions they've added which manage and modify certain VM control blocks and stuff like that. And so you can go into the manual and you can read up on how you create your own virtual machine, your own hypervisor essentially, right? In order to manage virtual machines. So, all of that implementation, all the things you would need to know how to implement something like a, VMware or Parallels or whatever else, it's all just in the Intel manual. And then 64, 16-bit modes, etc. So, all right. So now we're going to see a little bit of description of how you read the manual pages for something like, or just regular instruction, right? So I've given you my description of what the end instruction is. But now we're going to go and see what the manual describes it and how you interpret its description of the manual. And so you actually have to read the manual to read the manual. There is this section 2A, section 3.1. I mean, it could be a different number in your versions, but you have to read that first, and that'll tell you how to interpret the rest. But I'm going to give you my little summary. So here's a simple instruction that we know is pretty easy, right? AND instruction. And here I said you can have destination operand can be an ARM32 or a register. And the source can be an ARM32, a register, or an immediate, right? So we've got some combination of these other than you can't have ARM32 and ARM32. This is what the Intel manual says, right? So there's a bunch of different forms, and you have to be able to know how to come in here and say, what am I looking for? Like, I want to move an immediate to, an immediate to EAX, or I want to move an immediate to just any arbitrary memory, something like that. And then once you find the form that you want, then you can figure out like what bytes it requires, etc. So we'll go through this kind of line by line. So the first thing, just slicing this down to a little subsection of the very beginning of the manual page. We have what looks like 4 different versions of the assembly and instruction dealing with different sizes. So we have an immediate, whatever. But this last 4th one, we're not going to care about that. That's the 64-bit size. This is using this RAX. That's the 64-bit version of EAX. So we're not going to care about any of this because it's 64-bit. So cancel that out. And so now we're going to focus on these first, what look like 3 forms, but which are actually kind of 2 forms, but which are actually kind of 3 forms. All right, so the first column is the opcode column. So this is where I said, the behind the scenes, there's going to be some sequence of bytes which actually specifies how you encode an instruction, right? So for these AND things, they either start with 24 or 25. And then they're either followed by an immediate byte, this IB, immediate byte, or an immediate word, or an immediate D word. So I said before, immediates are those numbers which are hard-coded into the instruction stream. So I could see like 24. So I guess I say right here, if I saw, if like the very first thing in my instruction stream was 24, and then I saw 25, I would think this is an AND, 25 with AL, something like that, right? Because this immediate byte is being ANDed with AL. I skipping ahead, but we'll get there. So this is just saying when you see a 24, you should expect 1 byte immediately after that, because that's an immediate byte. And if you see a 25 as the first byte, it could be 2 bytes next or it could be 4 bytes next, and we'll talk about which it is and why it would be either one of those next. Yeah, so I guess I talked about it already. All right, so here's the problem, right? We have ambiguity. If I'm a disassembler and I'm walking down my instruction stream, and the very first instruction I get to starts with 25. Okay, I know it's an AND instruction, but how do I know whether the next 2 bytes or the next 4 bytes are still part of this instruction, right? Is this instruction 3 bytes long or is it 5 bytes long? Right? I don't know just based on this, because it's saying, well, 25 can either specify ending with 2 bytes or ending with 4 bytes. And so the simple explanation which I'll give, basically, which I think we get a little more detailed in the next class. The simple explanation is basically this version right here, this 25 with the 2-byte version, that was the original 16-bit version when Intel was still a 16-bit processor, right? And so nowadays we're 32 bits. And so when the processor is running in 32-bit mode, you should be expecting this 25 to be interpreted like a 32-bit immediate afterwards. So if the processor is 32-bit mode, treat the resulting immediate like a 32. Otherwise, if the processor is in 16-bit mode, treat the next thing like it's going to be 16 bits. And so when the processor restarts, for instance, if you reboot your CPU, processor starts in the 16-bit mode, and that's kind of like what DOS and things like those ran in. But then eventually the operating system bootstraps itself into a 32-bit mode, and that's what Windows runs in. So this is my, high-level, wishy-washy kind of explanation, but you should just think that like in a normal operating system, it's bootstrapped itself into 32-bit mode, and only like immediately after something's rebooted is it in 16-bit mode. So whether it's 16 or 32, that's how the processor interprets these. And then basically, as far as the disassembler is interpreting it, right? If you're IDA Pro, you basically just have to ask the user when they start it. You say, do you want me to interpret this as if it were 16-bit assembly, like as if the processor was in 16-bit mode? Or do you want me to interpret this like it's 32-bit assembly? And most of the time, you're looking at Windows binaries. Windows runs in 32-bit mode, so usually you're disassembling at 32. Therefore, IDA would come along, see, 25, and it would know the next 4 bytes, that's going to be an immediate. And now I'm going to go to the next byte after those 4 bytes and find out whatever instruction that is next. That's kind of how a disassembler would disambiguate that. They basically leave it on you and say, what do you want me to do? You want to pretend we're in 32-bit mode or pretend we're in 16-bit mode? Because we're not actually running if we're disassembling, right? We're just trying to interpret. The CPU knows what mode it's in, so the CPU knows which way it's going to interpret it. All right. So if you want to see, the code bytes and things like that, in Visual Studio, when you're in disassembly mode, you can like right-click, and we had the options like show symbol names, and I had us turn off symbol names at one point. You can also go ahead and show code bytes, and then that'll show you if you have push EVP, that's 55. If you have move ESP to EVP, move EVP to ESP. Never remember that. See, this is the problem with AT&T syntax. It just, if you know there's this one way and the other way, you can't like always just think of something like one way. So if you move ESP to EVP, that's going to be that 89E5. All right. And I can't find a good way in GDB to actually show the code bytes. So typically what I do, so one way you could do that is just use objdump. Right, so objdump did it. You just have a copy of objdump off to the side. That'll show you the code bytes. Otherwise, if you're actually like in GDB at the time, I would do something like, okay, well, here's main's address, and I want to see, what the code bytes are for push EVP. The problem is, if I do this, I don't know like how big it is, right? So I can do x/5 hex byte, and then like the address of main or something like that. Okay, and that shows me 5 bytes, right? And I know there's 5 bytes there, but I don't know that like the first byte is the push EBP, and the second 2 bytes are, that. So there's probably a way, I just don't know it, how to show the. So I've looked it up, and I've seen ways that it says should work, but they never work. I guess this is a new VM, so I should go look it up again and see if it works with this one. But anyways, that's what ObjDump's for. Except for those of you who have to do the hard version in the lab later. ObjDump will help you not. No, it will, unless you do the extra hard version. So, all right. Anyways, all right. So that's the first column, opcode. Right? The actual opcode is just, this first part of the byte, and then we're saying then there's going to be some extra bytes tacked onto it. Instruction, this is sort of like how you as a human interpret this thing, like what it's going to be displayed as by a disassembler or, a debugger, etc. And so this is what we've been looking at thus far. Instruction is just something like, so you fill in this immediate 32, for instance, right? So it's going to be and EAX and then, 0x FFFF 1, 2, 3, whatever. So it could be either like that, or it could be, a 1 byte version and AL and then hex FF or something. And this RM32 that I've been talking about thus far, you don't see it here, right? But when we expand our view of the manual page, the RM32 comes from this column, basically. You'll see RM32 in this column, and that'll be your little key indicator to say this value, which could be on this side of the instruction, could be, memory or a register, for that format that we talked about. 64-bit mode column, we don't care about this because we don't care about 64-bit, but it's just telling you whether or not the opcode is still valid in 64-bit. Compatibility or legacy mode is, again, something we don't care about. Just telling you whether or not an opcode is valid in 32 or 16-bit mode. Like if you have an actual new 64-bit thing, is that backwards compatible, for instance. All right, and then the description is just a little simple description. This is where, for instance, if we go to the jump instructions, this is where it'll say jump not equal is jump if the 0 flag, is 0, something like that. So this is going to be a simple little description, and now we're actually using infix operators, if you will, right? So EAX and 0x FFFF. All right, so now here's an example of AND where we actually start using the RM32. So I just moved down, I slid down our little window a little bit in the multiple forms of AND that exist there. And so I said, okay, there's a couple forms. We have one that starts with hex 80 and then another that starts with 81. And we see, again, this is just one where there's ambiguity. It could be a 16-bit version or a 32-bit version, but just assume it's going to be the 32-bit version for anything you're going to see most of the time, right? Unless you're disassembling DOS things, something like that. All right, so we have AND with an immediate and then an RM8. And so this is just saying I'm going to have some sort of address which, specifies memory, and I'm going to go out to that address. I'm going to pull in that value. I'm going to AND it with the immediate, and then I'm going to store that back out to that address, right? And I'm pulling in 1 byte because this is a byte. It's an RM8, right? So it's saying I'm going to have some 8-bit sized thing, and I'm going to have an 8-bit sized immediate. I'm going to AND them together, and then I'm going to save them back out to that same place that I got that byte from in the first place. Right. So that's the roughness here. That's the rough idea here with these RM32s and RM16s and RM8s and stuff in this instruction column. But then we have, if we want to know how do I specify in bytes this, if I want to write and, brackets EAX 0x FFFF00 or something like that, how do I actually specify those bytes? Well, it starts with 81, and then there's something, this /4, we don't know what that is, and then it's followed by 4 immediate bytes hard-coded into the instruction. So the question is, what is that /4? And unfortunately, I can't get into that in this class because I have to go then show you multiple tables, and this is why I've treated the RM32. I just call it like, an RM32, but it's really, this /4, for instance, could be 1 byte, it could be 2 bytes, and the combination of those are what lead to those increasingly complicated base plus scale, index times scale plus displacement, right? So a simple form of that might just be 1 byte, but if I want to then get complicated, then it may turn into 2 bytes plus a displacement or something like that. So that's why I'm not going to get into that here. Yep?
So I noticed that there are a couple of commands that have the same initial opcode,
Yep.
like jump and call, that are distinguished by the /3/4/5.
Exactly.
So that's actually data in bytes that follow the FF that we could look for? Or
Right. And
okay.
so if I went to this table and I told you how to like look things up in this table that I don't want to go into, right? So exactly. Like she said, you can have things where the only difference between instructions is whether this is a /4 or a /3, something like that, right? And so what these /4 and /3 is, there's some table, and this can also be like a /R. There's a table, and it says if this is a /R, you are allowed to pick any byte from this table. If this is a /3, you may only pick things from this column. If this is a /4, you may only pick things from this column. So that's where the difference comes. So a call and a jump may start out with the same 2 bytes, but then if the next byte is a byte which is only in this one column of this other table, you know this must be a call or a jump, right? And if it's in this one, it must be the other thing. So I can post that at the end, and I'll let you guys get working on your thing before I go into that, but basically that's more complicated than you need to get in Intro x86 class. I didn't bother to learn that until, I wanted to explain it in detail to you, and then I was like, I can't do it in this class. So. And so if we went to the man page, right, we had that table here first, right? This. We have this table, and that's the initial thing. This is telling you all the different forms which are valid, right? So I just covered a couple of them. I said I have an immediate that can go into EAX. I have an immediate which can go into just some arbitrary RM32, right? So I didn't tell you about this form when I had my simplified version. I didn't see it necessary to say that there is like a special form just to put it in EAX, because EAX is the accumulator register, and maybe we want to like put stuff in the EAX. So there's one form where you always put it into EAX. There's another form where you can put it into any register, just some RM32. But that's a longer form, first of all. So that's kind of the only real difference here, right? This form can potentially be pretty long, whereas this form is like definitely just 25 followed by the immediate. This form, it must be at least 2 bytes followed by the immediate, because this /4 has to turn into at least 1 byte, but it could turn into more bytes than that. So the simple form is smaller, like the limited form where you always go to EAX, that's smaller in terms of bytes. So if the compiler is trying to optimize based on size, maybe it would choose EAX in order to use that smaller form. But otherwise, there's the generic, just move into any old RM32. And then we have forms like take R8, so this is like a register, move that into an RM8, okay? So if you need to move a byte from one register like AL into some arbitrary other register like CL, right? So for those EAX, EBX, ECX, EDX, right? They all had versions which were AX, BX, CX, AL, AH, BL, BH, etc. So if you want to move from one register, let's say BL, into either another register that's 8 bits or some memory location, and there's another form, etc. So, yeah. Oh, and then finally at the bottom right, we have a form that has an RM32 on the other side, right? So you can take from memory. So you take some register, AND it with a memory location, and put it back into the register. So this basically, the groupings of these basically is telling you what all the possible valid forms are. So as many unique combinations of these there are, that's how many AND types you have. So anyways, after that table in the first part of looking at the manual, then there'll typically be like a description which explains the exact details of the instruction, any caveats, etc. It'll say, for instance, maybe this can or can't be used with the lock prefix. We didn't talk about the lock prefix, but it's basically just a way to like lock down the memory bus to provide mutual exclusion. So if I throw like a lock in front of an instruction, it says like the memory bus may not be used by anyone else while I'm doing this move to memory or something, so that you don't like start your AND and you pulled something from memory and then you had a register and you wanted to AND them together, but oh hey, you know, it turns out like memory changed between when you were trying to get it out and put it back in or something like that. So lock is just a way to lock down for mutual exclusion. It's just a prefix that can be added onto certain instructions, and like the details may tell you, you can use this with lock, you can use this with rep, right? We saw rep before, that sort of thing. And then it'll tell you, you know, all the different flags that this can or will set or won't set, right? Like here it's saying, unconditionally, when you do an AND instruction, the overflow flag will be cleared, and the carry flag will be cleared. So it's saying, you know, whatever they were before, it doesn't matter because afterwards I'm setting them to 0. So this is where, you know, if you really care what can all happen with flag setting and things like that, you have to go into the manual and you have to look into what can happen.
Does the lock guarantee that a certain line or chunk of code is executed without interruption? Or
I wouldn't say it's, no, I don't think it's without interruption. It's the memory bus cannot be used by any other, so if you have multiple CPUs, right, it's basically locking down the memory bus saying no one else may read from memory until this instruction is done.
so if you're like in your critical region.
Exactly. It's exactly for critical region type things. In operating systems class, when you want to make a mutex, you got to use the lock instruction in front of some sort of thing like an exchange or something like that. So exactly. It's for critical regions at the lowest level of like assembly instructions, basically. Because if you know, you can say, oh, well, this is my critical region and I grabbed my mutex here and I let go of my mutex there, right? That's at the C level, right? But what about that actual grabbing the mutex, right? That in and of itself is something which can potentially be preempted in the middle as all the stuff's going on behind the scenes in the hardware. So anyways, here's that JCC, one of those 4 pages of jump variants that I talked about. And so I just wanted to point out that, you know, one, you can definitely say that things are equivalent if they have, for instance, the same opcode, right? You may have different instructions, different ways to name an instruction, but something like, you know, jump if equal, well, let's see if they're on even the same page. Something that's on the same page. Find 2 that are the same thing. 72 and 72, all right? 72 here says it's a jump below. 72 here says it's a jump if carry flag is set. All right, so now we have at least some notion of what below means to the hardware. Below means carry flag equals 1, because these are the same exact instruction saying jump below. You would go over here and it says jump short if below. And it says in parentheses, well, to me, below means carry flag equals 1. And you have just a different mnemonic where you could instead say jump if carry. So that's where I was saying before, you know, when we have like those compares and we want to like put that abstract box between them and we say, okay, what's the next conditional jump? Is it a jump below? We'd put like a greater than sign. If instead we wanted to go through and figure out, you know, what flags does this compare set, because what flags would the subtract have set, then we could say, okay, did the subtract set the carry flag? Which it would, basically, if it had to borrow 1, I think. And so if you want to do things straight up based on flags, then this will tell you what all the flags are that are checked when you're going to do some jump. But most of the time, like I said, I find it easier to think about below and above and less than or equal to and stuff like that. And again, just some other examples. 77 is jump above. 77 is also jump if not below or equal, right? So above, same thing as not below or equal. And above, again, is signed, unsigned, right? Above and below are unsigned notions. Less than or equal are signed notions. And again, which mnemonic is actually displayed is entirely disassembler dependent, right? The disassembler just says, well, I see a 77. As far as I'm concerned, that's a jump above. And another disassembler may say, if I see a 77, that's a jump not below equal. There's really no rhyme or reason to that. That's just whoever coded up the disassembler, they got to choose what they wanted to display stuff as. All right. Now, did I go like too long? What time did we come back from lunch? So it's like almost 3. Did I give you a break at 2? Did I? Okay, good. All right. We're going to keep going. Here's just an example. So last night, I asked you to do the homework where you go find some new instructions. And so the utility of going and reading the manual is for those sort of cases where you're just playing around, you want to find some new instructions, you want to figure out what is this doing. Like, so I created a new instruction by some combination of C code, and what's the purpose of this? What is it actually doing? Well, actually, Dave, I should say that behind the scenes, I looked up that 99 for yours, and it's not actually a clear thing, right? So this is, I'll now do 2 examples of this based on the new instructions that came in today. We'll just start with this here. So if we go back to example 6, like one easy way that you can potentially get new instructions is just playing with signedness or unsignedness, right? Because I said the hardware doesn't care. The compiler is in charge of generating the correct instruction sequence so that it actually outputs something which maintains signedness or doesn't care about it, right? So originally I had unsigned into A, B, C, and we just did like a multiply and divide, and those turned into shift right and shift left, right? If I turn those into integers, so signed numbers now, and I'm doing a multiply or divide, now the hardware has to generate instructions that say, well, if this A, B, or C turns out to be some negative number, and I'm like dividing the negative number, so I'm shifting it right, I want to make sure that it like doesn't have those zeros put in at the top. Because if I, so if I have some negative number, if I have a signed number and it happens to be negative, like we'll say the most negative number, which was, 8,000,000,000, right? That was negative 2 billion, whatever. So negative 2 billion, right? So in binary, that's 1, 0, 0, 0, dot, 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 right? Bunch of zeros. Take each of those, turn those into 4 zeros, right? If I have this negative 2 billion, and I want to divide this, I want to shift this. If I shift this by 2, it better not be 0, 0, 1, 0, 0, 0, 0, 0, right? Because negative 2 billion divided by 2 better be negative 1 billion. Or, well, that was divided by 4. So let's turn that into a divide by 2. Just move it one place, right? Negative 2 billion divided by 2 better be negative 1 billion. And if I put a 0 up here, that's definitely not a negative thing anymore, is it? Right? But if I put a 1 up here, it turns out that is a negative 1 billion still. So this is where we get into, I already kind of said this already yesterday, but if I change from signed to unsigned, all the assembly instructions are the same, but in GCC at least, it'll generate this shift arithmetic right. So it actually, even for the multiplies, the shift lefts, it doesn't care. Because shift arithmetic versus logical left is the same thing. But for shifting right, when we're dividing things, we want to make sure that we're using this arithmetic shift. And so whereas I said before, the shift logical right just sticks a 0 at the top bit whenever you move it over, the shift arithmetic right says, what is your top bit right now? For the 8, the top bit is the 1. And it says, if I'm going to shift you X number of places to the right, I'm going to give you X number of 1s in the most significant bit, so that you, which were a negative number, stay a negative number. Because if I start putting zeros up there, you're not negative anymore. Got to keep the 1, 1, and keep moving it over. So that's one way you could like find a new instruction. And so here, if we found that we had this new SAR, right, and we wanted to figure out, okay, if we generated SAR, what's up with that? That's how. What's up with that SAR? Well, then we would go and we would try to find it in the manual. We'd find a page like this, and this turns out to be both shift arithmetic left, shift arithmetic right, shift logical left, shift logical right. It just calls it shift. Up to you to figure out which is which. Actually, it probably says in the description. But this is the full description. And let's see. Well, and I find the rest of this boring, so I'm not going to get into it anymore. I already told you, basically, basically the only difference with it, right? If you went in through here and you like looked at the actual, well, I guess what I was saying here was, hooray, we learned a new instruction, whatever number this is, 25. So we now know shift arithmetic right. The only difference with this thing is, right, we put ones. If the most significant bit was 1, we're going to put ones in as we shift over, right? With a shift logical right, we would put zeros always. We just put zeros as the most significant bits for each shift. And then you can go and read this on your own time, the detailed description of why exactly it makes like 5 more instructions when we're doing it signed. All right. Variable length instruction. See what else we got here. Okay, good. Okay, one last thing I want to talk about before we get into the choose your own adventure portion of this. So variable length instructions, we already talked about this a little bit. We said, so now we know that behind the scenes, these instructions can be specified by 1 byte, 2 bytes, right? So push EBP, 1 byte. Move EBP to ESP, 2 bytes. So this kind of has some interesting implications for security things. Most importantly, like the point here is, if you jump into the middle of some instruction stream, right? If you somehow get the EIP to just like point at some place that is not actually the beginning of the instruction, CPU is not going to care. It's just going to say, I see this first byte is whatever, you know, that's the opcode for whatever instruction. Therefore, I know now I have like 1 or 2 bytes afterwards, and then I have an immediate afterwards, etc. So the CPU really doesn't care, right? That goes back to all of our, you know, von Neumann architecture, so that I can act like I'm cool because I know von Neumann architecture. Data is code, code is data, right? The CPU doesn't care. It'll execute data just like it's code. It'll just interpret it as a sequence of bytes because we said our code behind the scenes is just a sequence of bytes. So, one issue here is, well, let's say one very simple issue is, let's say I'm at an instruction and I want to figure out what was the previous instruction immediately before it. I have absolutely no way of figuring that out other than brute forcing it, right? So I have some instruction stream. Here I am in GDB. I'm going to, you know, all right, so here I am at some random instruction. And I know that the instruction I'm looking at right now at this address right here, ending in BF, that's a pop EBP. Great. What's the previous instruction? Right? Okay. Was the previous instruction 1 byte before? Did it start at BF? Well, let's find out. I'm going to go ahead and take that address, copy it, x/10i. And then I'm going to put that address. And so I'm going to say, starting 1 byte before me, disassemble this, right? Except I didn't subtract 1. Starting 1 byte before me. Well, I'm even going to do it like this, -1, right? Okay. When I did that, the instruction stream, it says, the correct instruction stream is pop EBP return. If I start 1 byte before me, now it's telling me that the instruction stream is OR AL with 5D and then return, right? So that didn't tell me the instruction before me. That like modified what instruction I am, and that can't be correct, right? So -2. Okay, now I have an INC and an OR. Well, I still don't have the instruction which I know I'm at right now, right? I know that I'm at a pop EBP. So any sort of disassembly that doesn't tell me pop EBP is probably wrong. -3. Okay. Now I got something. I got add, and then I got pop EBP. So maybe that's right. Maybe there's an add instruction immediately before pop EBP. Or maybe it's not right. Right? Maybe let's keep going back. oh, well, okay, so add and then add. Okay, well, that seems like maybe now I have a little bit of confirmation, right? So I have at least two things that tell me if I just keep going back, eventually they keep saying that there's an add right before me. But maybe there's not. So I don't know. So the point is, I could just keep doing things like this, and maybe eventually I could find something that gives me a completely different instruction immediately before the push EBP, pop EBP, rather. Where's that at? Now I'm very curious if I can find something different. It's within the realm of possibility, but it probably won't happen. So anyways, this whole multi-byte instruction thing means that for any given memory address, even if I know that that is code there somewhere, I know this range is code, something is code there. I can't say necessarily where the instruction stream begins. Like if I don't have something that says like, well, they're jumping to that right there. Okay, well, if they're jumping to that, that's probably where the instruction stream begins, right? But if I don't have any sort of frame of reference, and I know like a bunch of the blob of data is code, I can't necessarily say what the real code is, right? Because I can interpret it different ways depending on where I start. And the first byte may not necessarily be the best place to start. So anyways, this has a few implications like that, basically. Remember, back in those RISC architectures, they were all nice. RISC architectures, as long as it's aligned by 4, these 4-byte instructions, starting at 0, right? 0, 4, 8. So you could always say if something's aligned on 4, that's the instruction that we're looking at right now. So this is, again, just an example of that. I can print 5 instructions starting at EIP, and this will tell me this is my, correct instruction stream right here. It's all in green. If I do EIP plus 1, I'll get 3 instructions which are wrong, but then eventually the next 2 instructions turn out to be right somehow. They eventually resynchronize. If I do EIP plus 2, I get 2 instructions which are wrong, and then eventually, I get back to the correct stream. If I do EIP plus 6, that somehow lands me at a sequence of bytes which eventually ends up in some bytes which cannot possibly be instructions. And so that's definitely wrong, right? And it turns out that these are like FFs, which are not valid instruction bytes. So this kind of has some implications for doing things like, let's say you wanted to find out whether some code, let's say that you're worried about a buffer overflow and you think someone may be copying instructions into this data buffer and they're going to like jump into this buffer after a buffer overflow. If you could potentially like disassemble them and like look at them, then maybe you'd say, well, this really looks like a normal sequence of assembly instructions and you'd like to stop that. There are some things that try to do that. I've seen some vendors which claim to have patents on things which do speculative disassembly of buffers in order to see, is there any shellcode in there? Yeah. So anyways, all right. So this is the end of the basic stuff. This is where you better ask me some questions or you better know everything. So who's got questions? Anyone on the phone have questions? Anything from any section that you'd like to go over again? How do you feel about a quiz? Feeling good? Yeah? Well, I don't have a quiz, so lucky you. All right, if there's no questions, ask me no questions, I'll tell you no lies. 5-minute break. Come back, we're going to let you choose your